I'm going to make my part short. My name is Denny Lee. I'm a developer advocate here based out of Seattle, Washington. It is slightly cloudy as expected. But saying this, I did want to go ahead and introduce Brooke Wenig, actually have her introduce herself for today's interview. This is going to be a very informal style interview. So we're just going to be asking questions very much on background and of course the machine learning story. Saying this, if you do have any additional questions that you would like to chime in, please go ahead and plop them in the Q&A channel below, so that way we can go ahead and listen. And so go ahead, Brooke, introduce yourself, please.
Hello, everyone. My name is Brooke Wenig. I lead the machine learning practice team at Databricks. Right now, I am based out of Marin County. For those of you who don't know where that is, it's the northern side of the Golden Gate Bridge.
Rock on. So, Brooke, before we dive into some of the pain and issues that you've run into when it comes to machine learning, I want to get a little bit about your backstory, a little bit about why did you even get into machine learning and data science in the first place? Why don't we start off with that?
Yeah, so I went to UCLA for undergrad and I was studying computer science, and I had a fantastic internship at Splunk. I was doing some front-end web dev. Following summer, I wanted to go back, join the machine learning team at Splunk. I was told they don't take interns, but how about you do this back-end C++ role? I thought that was fantastic. All of my schooling was in C and C++. And I show up for my second internship at Splunk, and I find out my manager's on paternity leave. So no warning, I just get this guy named Adam and says, hey, I'm Adam. I'm here to look after you for a few weeks while Chris is out. I lead the machine learning team at Splunk. And he was like, I don't have any project for you to work on. You know nothing about machine learning, but here, take these 4 weeks, go through these online classes and resources, and let's see what you can produce. And so that was my first introduction to machine learning. I was taking all these online classes on linear algebra, statistics, Andrew Ng's Coursera class. And after the end of those 4 weeks, I finally felt like, hey, I have a basic understanding. I can help contribute to the machine learning toolkit that Splunk was building. And so my manager did eventually come back from paternity leave. I just stayed with the machine learning team, and we helped launch the first machine learning toolkit for Splunk. So it was a fantastic experience, and I'm super happy whenever people do take parental leave.
Well, it is slightly important to do it anyways, but it had the additional benefit of allowing you to dive into data science. Okay, well then, okay, so you're at UCLA
Yep.
and a Bruins, which interestingly was funny when you told me, by the way, just to give you some background, I'm formerly Canadian. So when she told me she was a Bruins, I went ahead and completely went nuts because I'm a Montreal Canadiens fan. And then basically this tells you a complete context switch is all wrong here. So my apology for that. But then I'm curious, how did you go from UCLA to joining Databricks in that case? Because, you know, you're not a Stanford or Berkeley alum. So, no, and I'm just joking, by the way. I'm joking for everybody who's not a Stanford Berkeley alum there.
Yeah, it's a little bit of the backstory on Spark. Spark came out of the AMP lab at UC Berkeley. So a lot of the folks that joined Databricks are from UC Berkeley. A lot of our co-founders are Berkeley and Stanford professors. So how I got into Databricks was during this very same internship at Splunk, they asked me to look into Spark. So as part of building this machine learning toolkit for building machine learning models on top of Splunk logs, they wanted to do something sort of like what Spark sklearn ended up becoming, where you use Spark to parallelize the hyperparameter evaluation for different scikit-learn models. So I started taking the MOOC that Databricks offered. It was the distributed machine learning MOOC. And the professor that was running it was a guy named Amit Talwalkar. And I noticed that he had UCLA under his slide intro. So I reached out to him, and turns out he had just transferred from Berkeley to UCLA to teach machine learning courses. Asked him if I could sit in on his grad classes. He said yes. So I took his grad classes while I was an undergrad, ended up actually TAing the next round of the MOOC. And then when I did my master's, he was my advisor. So that was how I initially started working for Databricks in a part-time role, helping come out with these new online courses. Once I finished up at UCLA, then I had joined Databricks full-time as a professional services consultant.
Cool, rock on. I'm just curious, this is actually a follow-up to one of the questions that came from the Q&A. What were some of in addition to the MOOC itself, were there any good resources that you liked working with when it came to like learning about machine learning, data science? And the follow-up question, which is coming from me, did you actually have to learn the math for data science, which is a common enough question. So I figured I'd ask it.
Yeah, so a lot of the resources I went through were much more grounded in the mathematical approach. I think how people teach machine learning has shifted over the years. So I really liked a class from Stanford. It was called Statistical Learning. It's through Lagunitas. I don't know if they're still offering that course, but I really liked that one since it was actually taught by the creators of a lot of the machine learning algorithms themselves. So you have Tib Shirani, Rob Freeman, et cetera. So like the creators of the random forest are teaching you about random forests. And so I liked it because it was also a very informal environment. The two of them were going back and forth. They were interviewing the inventors of S and R, et cetera. So I really enjoyed that class. In terms of resources that I recommend now and how it's kind of shifted, I really like the fast AI approach to machine learning. That one takes a notebook environment-based approach rather than a math-based approach. So it teaches you, let's see what a random forest looks like. Then let's dive into the math of how does it actually decide how to make the splits? How does it compute feature importance? Once you understand what feature importance actually means. FastAI is entirely free. It's run by the prior president of Kaggle, Jeremy Howard, and his wife, Rachel Thomas. And so I really enjoyed that environment. It's super popular. Everything is Python based, though now they are starting to have some things implemented in Swift for their deep learning courses.
Cool, cool, cool. Actually, there's another really good question that just popped up that I figure is very appropriate here. What was your learning curve into machine learning as you were trying to learn the stuff? You know, for example, like diving into statistics, diving into linear algebra, things of that nature.
Yeah, so I definitely started with statistics first. I think part of that was I had already taken statistics courses in college, but I hadn't taken any linear algebra. I remember linear algebra being very difficult to learn on my own. And when I was trying to learn linear regression, I came to this point of why is it XTX? Why not XXT? Why not XX? What is this T doing there? And so that was when I realized I really need to learn linear algebra, understand what a transpose is, understand how to compute the inverse. So I think it's important to understand the math, not necessarily implementing it yourself. Like I never have to compute a matrix inverse by hand, but it's useful to know that to compute the matrix inverse, it's on the order of OD cubed. That way, you know, if you have very high dimensional data, it's going to be very expensive to compute. Therefore, you know, you're going to have a scaling issue and you can't solve for the inverse directly. And so I actually found it very helpful to have an understanding of the math. Granted, for people that are just getting into data science, I actually recommend they apply the concepts first, then learn the math, because a lot of people get blocked at the stage of, I don't understand linear algebra. I don't have somebody that can tutor me or other folks in the lab that can help me out with it.
No, that's a really great call out. So basically what you're suggesting is the inverse of what typically people are doing, which is start playing with it first to see it actually live, and then actually recognize the fact that there is math involved. And then actually now you know how maybe this math is related to what you've actually been doing.
Exactly. Play with it. See, you're going to get some bad result when you fit your model. You don't understand why. You don't understand, oh, you have correlated features. Then go back and play with it. And so
Perfect.
I remember.
Go ahead. Sorry. No, go ahead.
I remember my first time learning about correlated features actually was I was trying to apply linear regression to a baseball data set. I was trying to predict the number of home runs somebody hit based off of the number of singles they got, doubles, triples, et cetera. So I built a simple linear regression model just using singles and doubles. Both of them had positive coefficients, but when I added in all three of the variables, suddenly like singles had a negative coefficient. And that didn't make sense to me. Like the more singles somebody hits, you'd think the more times they get on base, the more home runs they're going to get. And so that was when I started digging into the math a little bit more behind linear regression, understanding these are all correlated features.
Got it. Got it. So I'm just curious now that you've brought this up, what's the implication?
Well, so the implication is you need to understand how these different features relate to one another to be able to build an appropriate model. Because if you have lots of correlated factors, one of them will just go negative, let's say, to compensate for it. Like if I have your height in both inches and in centimeters, because you're a Canadian, you use both metric system and
true.
the imperial system, then when it solves for these equations, these two are perfectly linearly correlated. And so there's many different ways of solving for that. Do I set 2x to be 1, 1x to be the other? Or do I set the other one to be 3x, the other one to be 1x? Understanding the math behind it can really help you when you try to interpret these models downstream. Because that's the most common flaw I see with our customers is that they build these models, they think they perform great, but they don't actually inspect what's going on under the hood.
Got it. Got it. Makes a ton of sense. Okay. Well, then let's shift gears a little bit. So now this is still going back in a little bit of history now. You've went ahead and joined Databricks. You're diving into machine learning and you're you're working with customers, whether it's training them or helping them solve their complex machine learning problems. I guess, can you start a little bit with that? Like some of the pains and gains, whether it was small scale or go right into distributed, whichever story that comes to mind first, I guess.
Yeah, so generally when our team gets involved and we help customers, it's one of two different scenarios. One scenario is they have an existing data science team. They're great with using single node tools, great at using pandas and scikit-learn, but they don't know how to scale it up with Spark. The other scenario is they have a great data engineering team that's invested in Spark, but they don't know how to build models and get insight out of their data. And so whenever we get involved, people are like, all right, we need to do distributed model training. We need to have everything run super fast, blah, blah, blah. But then oftentimes Spark ML isn't always the correct solution for them. And so some of the pains and gains that we have to go through with our customers are explaining to them what the trade-offs are. So with Spark, you're going to get super fast training time if you have large scale data, and you can use Spark ML models very easily for batch or for streaming applications. But if you need real-time model inference, like I need inference in sub 50 milliseconds, Spark ML is not going to cut that for you. And so some of the things that we have to work through with customers are understanding what are their deployment scenarios, because based off of that, that'll determine which models we can build. Based off of that, that determines which frameworks we can use. And so there's also hybrid solutions we can use as well with Spark. So distributed hyperparameter search, we can use Spark, but they could then get a scikit-learn model at the end of the day. But then of course that has the fundamental limitations of model and data still have to fit on a single machine.
Got it. So then I guess let's go backwards a little bit with the first scenario, right? Which is the folks that they know machine learning well, or at least they are familiar with it on a single environment, like using pandas, scikit-learn.
Yep.
What do you find when you're working with them, that is, like that was the pain to switching to more of a distributed model, i.e. the fact that the amount of data that they're dealing with end up going way outside the boundaries of a single machine?
Yeah, so when I see folks trying to first learn Spark, they often don't understand what's the method I should call. I know it's going to be called median in whatever language they want to, or whatever framework they want to use. In Spark, it's going to be called approx quantile if you want to compute the median. So the first thing they struggle with is methods are called different things or functions are called different things. Or even if they're defined in the same place, like head in pandas actually has a different behavior than head in a Spark data frame. Right. So they try to just do this one-for-one port and then they get different results. So let's say they figured out how to make the code run the way they want it to do. The next issue they hit is performance. And so you have to understand Spark a little bit better under the hood to understand what things are computationally expensive. It's like a wide versus a narrow transformation. You don't have to think about that with pandas because everything's done on a single machine. But with Spark, with a narrow transformation, everything can be done within that single partition. But with a wide transformation, you have to physically shift data across the executors. So like if I have an order by, I can't do that locally on one machine. I have to sort it locally and then sort it globally. And so understanding some of the Spark configurations as well, I found that a lot of customers just weren't aware of it. Once you make them aware of the Spark configs, then they're able to be much more effective.
Got it. So then related to that, which actually, this is a quick call out to your Spark and AI Summit presentation, keynote presentation. How did you find that maybe using Qualys actually both helped or maybe didn't help in some of those environments in which you're scaling from a single machine to distributed environments?
Yeah, so for the folks on the phone who aren't familiar with Qualys allows you to write your pandas code, but then scale it with Spark under the hood. So it's effectively just a wrapper to convert your pandas code to Spark code, and you'll get the same performance. So if you call head on a Qualys data frame, it will give you the same guarantees as head in a pandas data frame, but it's going to be running on Spark. So what I really like about Qualys is that oftentimes data scientists want to develop things locally on their laptop. They're going to be using pandas locally, then they switch to the cloud. They may or may not be using pandas, but then eventually they have to switch to Spark to apply it to massive scale. And in that conversion from pandas to Spark, lots of bugs, lots of errors creep in. And so with Qualys, you don't have to pay this conversion cost of taking all your pandas code and converting it to Spark. However, there are still some limitation of Qualys because Qualys can only support all of the pandas methods that can be supported from within Spark. So there's lots of things that you can do in pandas, especially with multi-indexes, that you just can't do within Spark right at this present time. And then also the Spark configurations also impact koalas. And I think that's the biggest, what's the word? Not quite misnomer, but biggest unknown for a lot of pandas users is what are these Spark configs that are going to be impacting my koala's performance? So things like Spark SQL shuffle partitions is going to be impacting your koala's performance just as it would your Spark performance.
Right. So then actually that's a very good segue to actually my next question related to the transition from single machine to distributed environments. Mm-hmm. Do you feel then one of the things that you end up spending time on is actually explaining all those data engineering concepts of how distributed environments work in the first place, right? Because it seems like you've got folks that they might understand the mathematics behind the algorithms that they're working on, but not necessarily understand how that translates to when you're implementing it in a distributed environment.
Yeah, definitely. And even the machine learning algorithms that you're taught in Coursera courses, they don't cover how they're done in a distributed setting. So with the Coursera courses, when you learn linear regression, you learn that X transpose X inverse, X transpose Y. That doesn't fly in a distributed setting because you might not even be able to store X on a single machine, let alone compute X transpose X or taking the inverse if D is really large. And so having a better understanding of how these systems work under the hood helps you understand what are the fundamental limitations. Like for the folks that love using decision trees, you might be upset that Spark ML, I believe the hard default is like depth of 30. You can't build a depth.
Yes, that's right. Yeah.
You can't build a decision tree with depth greater than 30, but that's because of the computational communication of doing a distributed decision tree. Whereas scikit-learn, you don't have that issue. So we do spend a lot of time educating our customers about how things differ in the single node scenario versus the distributed scenario. But more importantly, we tell them you will not get the same results. One's not necessarily better than the other, but just because you built a decision tree in scikit-learn doesn't mean you'll get the same results in Spark ML. And whenever we start our engagements, we always have to talk about what is success for the project. And so success generally breaks down into two different forms. One is our speed has to be faster than whatever they're running right now. The other one is whatever metric they pick, accuracy, F1 score, et cetera, has to be their score. And so we let them pick which one of these two is more important for them. And that's what we're going to try to optimize for.
Got it. So basically the quick call outs for everybody who are just joining or just to reiterate, you're the single environment versus distributed environment often will not necessarily have the same results, number one. And number two, the fact that you actually need to work with whoever is making the decisions. What is actually what's the success criteria? And that's not usually, and that's almost never I get the same results as a single machine result.
Yes, exactly. Yeah, there's tons of approximations that Spark has to do under the hood to speed up the computation. So like with decision trees, let's say, to speed up that computation, Spark has to discretize all of your continuous variables into bins. And so if you've ever looked at the Spark ML docs, you'll see a parameter called max bins. Spark ML has that parameter, but scikit-learn doesn't have that parameter. And so that's just one of the many reasons that you'll get different results is because it has to discretize it. So we can talk about for worker one, this split point, we're talking about the same value across all of the different workers. But scikit-learn will have different parameters that Spark ML doesn't support. And so one's not necessarily better than the other, but you will get slightly different results. They should be on the same order of magnitude. So I wouldn't expect a crazy difference in your scores, but just don't expect the exact same numerical response.
Got it. Perfect. Well then, okay. So this is a good transition. Let's flip it the other way around now, which is the folks that they happen to know Spark decently well, or at least distributed environments well. So they understand like, okay, I have shuffling, or my partitions are spread across multiple nodes, the potential impact of how, when you distribute data, how it has an impact on your query. So you don't have to explain that part of it. But then what's what you usually run into when you're trying to explain to folks how machine learning works when they may not necessarily have that background, but they happen to have that distributed background?
Okay. So whether or not they have a distributed background, I would still approach explaining what machine learning is to them in the same way. I actually like to start with asking them, what do you think machine learning is? Because answers will vary wildly. And oftentimes they're either too broad or too specific. They don't apply to all types of machine learning. And so I like to give them a few examples of machine learning and data science in everyday life. Like when you watch Netflix, how does it come up with what movies to recommend to you? Or when I am searching online for products I want to buy, how does it know what products would pair well with it? So starting with that and then breaking it down into the different types of machine learning. And even within types of machine learning, there's disagreement as to what constitutes machine learning as specific type. So there's supervised, unsupervised, nobody can test those two types of machine learning, but there's also reinforcement learning. And then there's also the argument to include semi-supervised machine learning. So there is also some ongoing evolution within the machine learning community as well.
Got it. So then typically when you're working with your customers, what is it that I guess the question that I'm thinking about is, what is it the most common like set of issues that you've run into first, like in terms of when you're dealing with a large enterprise that's used to the idea of having lots of data, but not used to the idea of like, how am I supposed to go ahead and make sense of the data? In other words, you've gotten past the point of like, okay, here's how machine learning works because I can give you movie recommendations a la Netflix. Mm-hmm. What are the usual issues that you run into? And I guess that where I'm hinting toward is that usually it's not the actual algorithm itself. It's usually, isn't it usually like them even understanding what their own data is in the first place?
Yes, hands down, the biggest blocker we have for any customer engagement is data access, actually. So getting access to the data that we need, and then also getting the domain expertise in the room with us, because oftentimes we're joining data sets from all different departments, and we need them to explain to us which data we can actually trust. Because if, let's say, the data is perfectly filled in, I never actually trust that there's no missing records. I want to ask, what were the data engineering pre-processing steps that led to this fully filled in data set? Because oftentimes the issue that we see that breaks down to data science is data engineers think they're helping out the data scientists by imputing all the missing values. And so when I build a model, works super well on the training data set. When I apply it into production, then suddenly it explodes. All of these errors because it doesn't know how to handle missing values. And so the first step is just understanding, how did the data get here? What's the documentation for all of the different processes we've taken to get it here? And then understanding the data itself, which fields we should trust, which fields we shouldn't trust, which fields will be available for us in the future, which ones we expect to be changing over time. Because sometimes I'm given a data set with 1,000 features and it's called like C0, C1, C2, C3. I have no idea what those features mean. Some of them I can guess what they mean if they have intuitive names like price, number of bedrooms, whatever it may be. But then it might not always be what you expect it to be. So also clarify, even if it seems obvious, make sure that there is some documentation describing what each of the features correspond to.
So yeah, you remind me of the old data warehousing context of like basically build a data dictionary. And then because the fact that one department's definition of color may in fact be a different definition altogether, like for using the textile industry example.
Yeah.
Right, exactly. They actually have very different definitions. So they use the same column name, but in fact it means two completely different contexts. Mm-hmm. So
yeah, or some things could just be redundant features because they think they're helping out the data scientists, like providing your height in feet and then converting it to centimeters. I really don't need both. Right. But sometimes they think that they're being helpful. And so that's where some of the disconnect comes down between data engineers and data scientists. If you impute those missing values and then the human analyst can't even tell what's the real value, what's the imputed value, how do you think the machine learning algorithm can discern between those two?
So it's interesting. So before we even get to talk about feature engineering or languages or anything else like that, you're actually sitting down, breaking down. The first thing you're doing seems to be breaking down the silos, just like getting everybody in the same room to actually talk. So how often, I'm just curious, how often do you find that you're walking into an environment where you don't need to do this actually?
The only time when we don't need to do that is when a company has a sufficiently large enough data science team. Oftentimes, most companies have data science, like 3 to 5 data scientist stops. But if we are ever in the case where we get to work with a team of like 30 data scientists, they've already taken care of a lot of that work for us. Okay, and so if that's the case, they have 30 data scientists, they just need help scaling out their solutions. And so it's a very different problem rather than trying to build the pipeline from scratch.
Actually, related to that, I'm curious, how many companies have you, or have you worked in any companies where they actually had a large data science team, but didn't have a data engineering team actually?
None come to my mind right now.
Okay, cool. No, the only reason I bring that up because so now I'm dating myself a little bit, but is because in fact in the past that's exactly what happened. I would walk into companies where they had this like decent sized data science team and had one data engineer, and they were wondering why their data was messed up. And I was like, Okay, well, I think I know your reason. Right? So, gotcha. So, okay, all right. Now let's switch gears a little bit. So now, irrelevant if you're talking about a company that's shifting from small to distributed, or they're distributed to actually learning machine learning, they're
Mhm.
at the point where you've broken down the silos. They
Mhm.
actually are all talking together. The data might actually be in decent state, or even if it isn't, you're beginning that progression to get them in decent state. Okay.
Mhm.
First things, which actually is a question, so I'm just going to ask it to you right now, which is like, but how about if I don't really have large amounts of data? Do I still really need distributed machine learning to do that?
So every company's definition of large is different, or small, medium, whatever it may be. Like for a company like Apple, like 10 gigabytes would be tiny data. But for a startup, that could be a large amount of data. So everybody, you just need to come up with a definition of what do you mean by large, what do you mean by small. Oftentimes I find that people are asking for distributed computing, but don't actually need it. This more comes up in the context of distributed neural network training rather than distributed machine learning. There's a pretty linear speed up between going from sklearn to SparkML, provided the same algorithm exists in place, yada yada. But that same does not actually apply to neural networks. There's so much communication going on. So if you only have like 1 gig of data, it's definitely not worth the hassle of doing distributed training for. It's one of those things where everybody's talking about it. They think everybody else is doing it, but nobody's actually really doing it. There's way better ways to speed up your computation rather than going to distributed setting, especially for things like deep learning. Get smarter about how you actually solve for the problem. So adjusting your learning rate, trying different values for trying different architectures, different optimizers, doing some hyperparameter tuning, and doing that all in a single node multi-GPU before getting to the distributed setting. So like I can count on one hand all the customers that I've worked with that are actually doing distributed deep learning. Whereas with machine learning, it's much more common to go into the distributed setting because of that linear speed up. And oftentimes they've already built the scikit-learn solution before they switch into SparkML.
Got it. So related to that with hyper, do you feel like, using things like the vast majority of customers actually really need to use like hyperparameter tuning, like hyperopt or Horvath trainer or Horvath runner or Horvath itself in their environment? Or do you feel that it's really, they need to get to a point where they're actually dealing with large enough data, truly large amounts of data, truly distributed environments before they actually want to switch to something like that then?
Yeah, so I'm going to separate, I'll talk about hyperprompt in a second, but speaking of
Okay.
Horvath, most
Yeah.
folks do not need to do distributed deep learning training because the difference with deep learning and machine learning is with deep learning, you only need to fit in one batch of data at a time. So a batch could be 64 data points. Whereas with machine learning, you have to load an entire partition in the case of SparkML, or if you're dealing with scikit-learn pandas, you need the entire data frame to fit around in memory. So with deep learning, given that you can continue to do all this training in an online manner, just loading in one batch of data at a time, that allows you to scale very differently than with SparkML. With SparkML, there's no concept of online training. If you want to keep training your model, you actually have to retrain it from scratch every single time. It can't take off from the last set of values that it had, whereas with deep learning, you can. And so oftentimes I see customers asking for Horvath, but when we get into the nitty gritty, we realize actually don't try to do Horvath with multiple CPUs, just do one large GPU instance. You can still run Horvath within that single VM, but with multiple GPUs. But you don't actually need to do a distributed setting. Going back to your question about hyperopt is a little bit different. That one allows you to search for different hyperparameter values, and that could be applicable whether it's scikit-learn, SparkML, single node neural network. So like I find hyperopt still to be a very valuable tool, but Horvath, a lot of folks ask for it, but I find that they don't actually need it.
Got it, got it. And then whether it's hyperopt or anything else for that matter, what do you see I'm just asking a question that just popped up here. What's the impact of actually utilizing GPUs in your environments?
So excellent question. So it depends whether you're doing machine learning or deep learning, which framework you're using as well. So with SparkML, it doesn't actually utilize any of the GPUs. It's still running on CPU. So I often see customers tend to over allocate resources that they're not actually using. Whereas with deep learning, there will be significant speedups from using GPUs over CPUs. And so even if they cost 10x more, if you can get to your results in a tenth of the time, that speedup will be worth it because your data scientists can be more productive. However, for inference, a lot of folks will still use CPUs for deep learning models because GPUs are super effective because they can do batch matrix multiplications. But if you're in an online scoring situation, you don't want to wait for 64 data points to be loaded before you make a prediction. So often for inference, people will still use CPUs, but for training, they'll use GPUs.
Gotcha. So perfect. So this actually is a good segue to actually our next issues. You've already hinted at this, but like any other, no, I'm sorry. You not only hinted, you've actually already explained some of this. But what are some of the other limitations when it comes to working with Spark MLlib? I mean, we know that it can be distributed really well. We know that it can be fast at times, and in those environments, it's great to work with. What are some of the other issues that you ran into when it works with like distributed ML, like and Spark? For example, a good example would be like random split, for example.
Okay. So thank you for seeding that one, pun intended.
Oh, no problem.
You'll see in a second. So yeah, some of the issues I've seen with customers is they think that Spark ML isn't reproducible. And so one of the reasons for that is there's this random split method in Spark. This isn't even part of Spark ML, just random split. How do you split your data into your training set and your test set? So data scientists will often do like an 80-20 split, train and test, set a seed of 42 because it's the answer to life. No other real reason why it's 42. You could pick one, you could pick your favorite number. Then they build their machine learning models. So they run it today, they get some value, let's say their RMSE is 100, they run it tomorrow and their RMSE is 120, and they have no idea why did it suddenly get worse. Turns out they changed their cluster configuration. It was either an auto-scaling cluster or they added nodes, removed nodes, and because how the Catalyst Optimizer works, it partitions your data based off of the size of the data and the underlying resources. The underlying resources changes, how your data gets partitions changes. So the random split itself is not reproducible from the day before since your cluster configuration changed. So if you keep your cluster configuration constant, you should be getting the same results. But my recommendation to customers, instead of doing this dynamic train test split every time, split the data once, write it to train and test directory separately. You never have to worry about this issue again. So that's one issue with reproducibility with Spark. The most common issue I see customers hit with Spark ML is they love some algorithm in scikit-learn or some other library like imbalanced learn, but Spark ML doesn't support it. And so they have to look at other ways of being able to distribute it. And so oftentimes they'll use something like a pandas UDF to be able to train each of those models independently on the workers. So they still get the distributed compute benefits from Spark, but they can't be training their models on massive amounts of data.
So actually, since you brought it up, why don't you, for the audience, clarify what a pandas UDF is in the first place?
Thank you, Denny. So pandas UDF, also known as a vectorized UDF, and a UDF is a user-defined function, allows you to execute any arbitrary function on your Spark executors. So instead of using any built-in functions, you can define your own custom function. And so with a regular UDF, you apply them one row at a time. So you deserialize the data out of Tungsten, which is Spark's internal in-memory binary format. You operate on that single row, serialize the results, send it back. And so there's a lot of overhead with this deserialization and serialization. So what the pandas UDF allows you to do is instead of deserializing and serializing one record at a time, it deserializes a batch of data and internally uses Apache Arrow under the hood for that. So you amortize this cost of serialization and deserialization by deserializing a batch. I believe the default is 1,000 or 10,000, something. I think it's 10,000 records at a time. Operate on that batch of 10,000, serialize that result back. And so what you can do with pandas UDFs are you can, let's say, train a custom model for every single customer. So there's different types of pandas UDFs. There's the scalar one, where you simply just do the same operation to every single record in your data frame, but it does it in batches of 10,000. The other one is a group map UDF. So let's say you want to group by customer ID, apply something, you could build a model for every single customer. And so I've seen quite a few of our customers combine this with MLflow. They group by for every customer, build a model, log that model to MLflow so they can pull it back whenever they need to for that given customer.
Perfect. Well, then that's actually an excellent segue to exactly the next question. How have you been, what is MLflow, since you brought it up, and how have you been using MLflow in your environments to make things better when it comes to managing your machine learning data lifecycle?
Yeah, so MLflow is an open source project created by Databricks, though most of the contributors are actually outside Databricks. And it's a way to manage the machine learning lifecycle. And so it has 4 main components: experiment tracking, projects, models, and the latest one is the model registry. Most of the customers today use it for experimentation. So the problem with data scientists is that we do things in a very ad hoc manner. We run our Jupyter notebooks, we run things out of order, and I give you my notebook and you're like, what the heck, this code doesn't even run. Because I ran I ran cell 7, then I ran cell 5, you don't know that. And so what MLflow allows data scientists to do is a way to reproduce their experiments. So it allows me to track all of the metrics from my model, allows me to track all the parameters. I can even track the data if I want to. So I could log the data as an artifact. I can log any matplotlib images, but it also tracks the notebook that generated that run. And so it's a way to be able to share my results with somebody else so they can reproduce them. And some other aspects of MLflow allow me to package up this run and all of its dependencies. So when I give my experiment over to Denny, he's not like, what are the 5 different libraries you use? Which version of TensorFlow was it? Was it 1.14, 2.1? So it allows me to package up all the dependencies to be able to run on other platforms as well.
Cool. Lots of great questions. Actually, I'm going to jump back to one other question, basically the pandas UDF, before I go back to MLflow, just because it's still on our minds.
Yep.
Do you see any significant difference when you're like trying to run something with a pandas UDF versus writing an algorithm using basically what's available in MLlib in Spark? I'm just curious if you've run into those issues.
So the general rule of thumb is if something's available in Spark, you should use the built-in one for Spark. The reason being is that whenever you write a UDF, it's opaque to the Catalyst optimizer. So it can't rearrange your query above or below that UDF. It treats it as a black box. So if it's available in MLlib, just use it in MLlib. The reason why you might not want to use MLlib is either your data set's small or for the end deployment. If you want to do real-time inference, MLlib is not the best solution. So in that case, I would use pandas UDFs. So it just depends on what you want to do. If you want to be doing inference versus training, if you're just trying to build one large model, I would go for MLlib. If you're trying to build a model per customer, I would probably err on the side of pandas UDF, depending on how much data you have per customer. Inference, it doesn't really matter as much because MLlib will automatically do distributed inference. Pandas UDFs will also do distributed inference. But any of the built-in methods would still be faster.
Got it. And then related to that, which both the pandas UDF and also MLflow in general, what are some of the challenges that you've run into in basically putting these ML models in production?
The biggest challenge
the high level. Don't.
Yeah.
Otherwise, this is a whole new session. Okay, I realize that. So I apologize for being that big. Sorry.
Yeah, so it's just getting sign off on getting the model into production is the hardest part. So making sure that there's a team in place to monitor the model, making sure there's a team in place to continually do testing on that model. So data scientists, we love building models. We love reporting our R square is like 0.98. It's fantastic, but we're not so great at taking it that next step of actually pushing it into production. I believe I recall reading a stat was like 1 out of 8 data science projects actually make it into production, or something even smaller than that.
Oh, fun. Okay.
Yeah, exactly. So it's, so what? I built this model. What are you going to do now that I built this model? And so I always like to ask that question at the beginning of the projects, in addition to what are your deployment requirements? What's success? So what? I built you the best cancer classifier model. How are you going to use this model?
Right.
Because a lot of data science projects will get stalled. There's one I worked on that's been stalled for over a year, actually, because they still don't have sign off for how they're going to manage and deploy this model, because the data science team doesn't want to take ownership of that. But now they're asking the data engineering team, who doesn't understand the complexities of it. And so just making sure that you get these teams to work together from the beginning to help put it into production.
So reoccurring theme, basically, it's all more times than not, it's the process and the people that are slowing things down, not the actual algorithm or the math behind it.
Exactly. Yep.
All right. Well, then related to that, I was not actually a purposeful segue, but it's actually ends up being a great segue since we're talking about people and the process. When you're working with AI, how do you address bias and regulations? Like, because there's often the issues of bias when it comes to the results of the data you're working with, or regulations that actually lead you in one direction or the other. How do you address that when you're working with machine learning models in general? And I realize that's also a vague question, so we'll probably need to break it down for the next 10 minutes.
Yeah, so there's been a lot of discussion lately in the ML and AI community about we have all of this bias in our results. And so some of these will come up with these face recognition systems. They perform very well on light-skinned men. They perform very poorly on dark-skinned women. So how do we ensure that these models will perform fairly across all of the individuals that they impact? Or also things like GDPR actually mandates with the right to explanation. If I apply for a loan, I'm denied, I have the right to ask why I was denied that loan. And so model interpretability keeps coming up with this, but taking a step back, a lot of the issues come up from lack of diversity and understanding of the data. And so Google had an issue with this a few years back with Google Photos. If you searched for a dog, it showed you photos of your dog. If you searched for a gorilla, it showed you images of Black people. And so a lot of this comes from not having diverse teams. Google publicly apologized for this, rightfully so, and said the issue they had was that less than 2% of their engineering team was identified as Black. And so even though there's all of this, even though there's lack of diversity working on these problems, it's getting people to think about how do these models impact the people that we're applying them to. And so Kathy O'Neill has a great book called Weapons of Math Destruction, talking about how the rich get served by people, the poor get served by algorithms. And so we really have to be looking into these models. What are they actually doing? And there's bias in our teams, sure. There's also bias in the data, but to me, it fundamentally stems from bias in regulation, because these regulations are what's causing all of the bias in our data. And even some of our older data sets we shouldn't be using because of this bias. Like if we were to take images of schools from way back in, let's say, the 30s, during times of segregation, we don't want to be using that for training our classifiers nowadays. So we have to be careful into looking into our data.
Gotcha.
Yeah.
So then how much of this can you programmatically basically put in place? Because what naturally, like, for example, a data science manager is going to ask is like, oh, I can programmatically put policies in place, versus how much of it you can do from the standpoint of education, like, in terms of what are the things that you think are the top 2 or 3 things that people need to do in order to be able to help address these things?
Yeah, so Timnit Gebru, she's a researcher from Stanford, has this awesome paper called Data Sheets for Data Sets, which is documenting how the data was collected, how is the data supposed to be used, documenting any assumptions or biases in the data. So this goes back to that earlier theme of we need to document all of the pre-processing steps we did to data. Even the step before that, we need to document what the original raw data is and what the data was actually intended to be used for. So that's one thing that we can do to combat some of these biases. The other one is in regulation itself, being more advocates for it. One thing that actually surprised me, I learned a few months ago, was about the car manufacturing industry. Up until 2011, they did not mandate to have female crash dummies when they were testing the safety of cars. They were only mandated to use the average male height and weight for the crash dummies. And so even though men were more likely to get into car accidents, for the equivalent conditions, women were 47% more likely to be injured. And the reason for that is that they weren't testing for this. And this stems back to a regulation issue. Furthermore, it wasn't just women, it was also children and obese people were more likely to be injured. And so by being advocates for changes in regulation, hopefully we'll see these measures come in, protect people that they're trying to serve. And so now they are mandated to use 50 percentile female crash dummies, but they're not required to use pregnant women crash dummies, which I actually found very surprising, because a lot of women, when they get into their later stages of pregnancy, need modifications done to the seatbelt to even fit in the car. How do you know that it's still gonna be safe for them to drive?
Gotcha. So then there seems to be this case of basically not just regulations, as you're calling out, or the people who are actually in charge of collecting the data need to actually go ahead and record or understand what the biases are. Mm-hmm. But then there's also the implication of, like, perhaps the data sets that they're working with, they have to go back and ensure that there isn't bias inside those data sets as well. It sort of reminds me of I believe it was the Udemy car data set that actually had, it was supposed to be supervised. And so, but then there actually, in fact, were many instances of pedestrians, children inside the car camera data set that they forgot to flag. So they were actually trying to go ahead and say, okay, like, will your algorithm go ahead and make sure that the car will stop? And in fact, it's completely missing a bicycle or missing a person or missing a child because they didn't tag the data correctly.
Yeah, exactly. And a lot of this goes back to ImageNet. It was a famous competition. I believe it came out in 2012, trying to classify images into one of 1,000 different categories. The majority of those images come from the Western world. And all of these different models that we build, BGD16, ResNet, et cetera, are all based off of this data set that is fundamentally very biased. And so whenever I build any image classifier technique, I do transfer learning on top of these models, which already have those inherent biases in place. So just propagating those issues. And so there's lots of different research these days about how we can remove some of the biases in ImageNet. A lot of other image data sets like labeled faces in the wild have a very explicit disclaimer saying, we have issues not representing all of the different groups in this data set.
Gotcha. So cool. So even after, it seems to me that even after presuming that you've figured out how to break down the silos, so people are actually working together, you've figured out actually when to use Spark MLlib versus when to use pandas, in your environments for whether it's training or for inference or whatever else. And presuming that you've even went ahead and got to the point where you've deployed it, right? And it's working. It seems to me that it's almost like this is just the beginning. You're going to have to constantly look at the data, see what the feedback is, and ensure that even if you weren't biased before, that there may be incurred bias as new data sets come in, or because the model's too old, or the fact is that you didn't take into account of, for sake of, just like you said, okay, we had a primarily Western data set, but now of course there's not a bunch of non-Western images coming in. That means your model is going to fail appropriately. So why? Because of bias.
Yeah, I mean, in addition to just monitoring for that type of bias, there is also the machine learning concept of bias and variance too.
Right.
And so in general, regardless of whether or not you're monitoring for bias in your data set, you still need to be monitoring your models to make sure that the distribution that your model is trained on is still relevant or represents the distribution of your test data as well. And so that's another common issue where machine learning models fail. Does super well in training data set, apply it to production, but then turns out the production data set looks wildly different. Like if I'm trying to build a cancer classifier and I'm building it off of patients that are already in the hospital versus the general population, that's going to have a very different distribution.
Gotcha. Perfect. Okay. Well, hey, there's about 3 minutes left. And so I believe we answered a sizable chunk of the questions that were in the Q&A panel. But I did want to leave it where if there's anything else that you'd like to add or to, give a hint on, and then we're going to also call out our session for tomorrow. So I just want to leave the last words with you in terms of machine learning best practices, some of the things that you think, if I forgot to ask you or forgot to call out during today's session, like what's the last word per se in terms of machine learning best practices that you would like people to remember?
Yeah, best practices, work with other people. That's the best way that you'll learn about new techniques. You'll learn the limitations or some of the flaws in how you approached a problem. So similar to how we always say, like, ensemble methods perform the best based off of results of Kaggle competitions, ensembles of people also perform the best for machine learning algorithms. So get different viewpoints. You'll learn from them about different ways of pre-processing your data, different research techniques. Maybe you try to approach a problem one way, but actually this other way be better. So just try to work with other people. That's the best way to get these models into production.
Perfect. I love it. Ensemble of, not just ensemble of algorithms, but ensemble of people. I love that. Cool. So I did want to, before Karen closes the show, I did want to call out that tomorrow we actually will be, originally we were planning to have an addressing GDPR CCPA session, but due to the current health and quarantine shelter in place, and make sure you wash your hands and cough correctly, by the way, folks, we actually going to be switching gears, and we're going to be talking about scalable data analysis of your COVID-19 data sets. There's actually at least 3 data sets on Kaggle, if not more, that are actually about COVID-19. And what we're going to do is actually start talking about that session tomorrow. So tomorrow at, Karen, you're going to correct me, but I believe it's 9 a.m. Pacific. We're going to be switching gears and talking about that. And we're actually going to create a set of workshops to follow up, to dive into each one of those data sets. So tomorrow's just more of a primer, just to give you an idea of what's going on. But then afterwards, we're going to create these workshops to dive deep into it. So to help accelerate and jumpstart your scalable data analysis of the COVID-19 data sets. So Karen, why don't you close it up if I missed anything else?
Oh, you're good. Thanks, Denny. Yeah, so everyone, I'll send out the link to join those upcoming Tech Talks and workshops. So make sure that you are in the Spark Global Meetup group, because I'll be messaging everybody the links, the recording to today's video, and then also the links to join the Tech Talk tomorrow and future events there. And also this recording will be available on YouTube Live. So thanks everyone for joining. Thank you again, Denny and Brooke, for your time. This was great, getting some good feedback in the chat and Q&A. So thanks thanks for sharing your feedback, and I hope you guys have a good rest of your day.
Thanks, everyone.
Thanks very much. Take
Bye.
care.
Bye.